Now, the measure that we're going to be considering today for gerrymandering is we are going to do pretty much what we were doing in the previous video. We're going to use the computer to take a map and assign districts according to our rules randomly. And our rule is going to be that the districts need to be contiguous. So we will have the computer create random contiguous districts of equal population size. Once we've created a random assignment, we will do the count just like we saw in Excel, where we say of these districts, who wins this district, a red representative or a blue representative, and we'll come up with a total to say something like, well, we had 100 people, we had 5 districts, and we had 3 blue representatives. We can determine everything we need to know from there. And then we will repeat that process a lot. So we will have the computer hundreds, thousands, millions, billions of times do this process of keeping the identical 60-40 split, so identical map, not changing what that is, although we'll start by attributing it randomly. And what we will have the computer do over and over again is create these random contiguous districts of equal population, and then perform that count on the number of representatives that results from that districting. So we'll do that process millions of billions of times on the same map. And then what we'll be able to do is draw a little graph of, well, how often did I get 0 blue representatives? How often did I get 1 blue representative? How often did I get 2 blue representatives? And we'll create probabilities for each of those scenarios, saying if we had a computer doing this, which had absolutely no bias and was doing everything 100% randomly, I can tell you how frequently we would expect to see each of those distributions. And if I've done it enough, that should be a good sample of what is going on in the world without personal interference. If we find that the map that we have, that a person drew, ends up leading to a representation that almost never came up in our random measure of things, then we're going to assume that that map has experienced personal influence and somebody had an agenda when they were looking at that map. They did not do it innocuously, because that's precisely what our computer is doing millions and billions of innocuous, unmotivated samplings. And if they're never coming up with a particular outcome and an individual happened to come up with that outcome, then we're going to call that gerrymandered, because it was not happening in our uninfluenced examples, and we did lots and lots of them. If a person came up with that, their argument that that just happened to be the way it all came out is a little bit of a ridiculous argument. So that's what we're going to do. We're just going to repeat this process of drawing districts over and over and counting representatives. The mathematics of that is not particularly hard in terms of the counting. What ends up being a very difficult mathematical problem is drawing the districts randomly with equal population in such a way that they are contiguous. That is a much more difficult mathematical problem than the counting of the probabilities. So in order to do that, we're going to have to use lots of tools at our disposal. The first thing that we're going to want to do is use something like Excel, which has one big strength, which is that it's very visual and it's very easy to graph things in and have Excel come up with patterns for us. So I've imagined that I have a 10 by 10 grid, and I am going to have that living here in B2 up through K11, and I want to number each one of the people in Simpletown in this very procedural way. So this is how I want to have my 100 people labeled. And you can tell that because Excel did that so quickly, that there's a pattern going on here to the way that I've numbered things, a very easy and natural pattern. But what I'm going to need to do in order to draw these districts is I'm going to imagine that this is my town, and I'm going to come up with the districts by starting in position 1 and taking a little random walk. and saying, okay, if I can only move in the cardinal directions, cell number 1 could either be connected to cell number 2 or to cell number 11. So I pick one of those directions at random, and then cell 11 is connected to these two other cells, cell 12 and cell 21. So let's pick a direction at random and go over there, and so on. And so we could imagine taking a random walk all around this simple town. And if we visit every single square and don't visit any square twice, we could come up with a big long chain of the numbers from 1 through 100. Maybe 1, 11, 12, 2, 3, 13, 23, so on. We could take this little random walk. And what we'll do is if we hit all of those numbers 1 through 100 without repeating anything, and where we've always chosen somewhere to go next according to what's adjacent to a particular cell, then we'll just divide up the numbers 1 through 100 in chunks of 5 and call those our districts. Now, the thing that's really tricky about that is that we're not going to want to program that on our own, just going 1 to 2 to 12 to 22 to 21 and so on. We could start doing that random walk, but because 11 was sort of blocked in that procedure, 11 would be left out if I moved away from 11 and went over this way. So just taking a random walk around here is going to have some problems. We might repeat some values, we might box in some values, we would have to backtrack. It's a really difficult mathematical problem. So what we're going to actually do is translate the numbers we see here into a very huge matrix, a 100 by 100 matrix. And what's going to go in that 100 by 100 matrix is the adjacency representation of this grid. So for example, we would want a matrix that tells us that the number 43 is connected to the numbers 33, 42, 44, and 53. And because we've labeled this in such a nice pattern, coming up with that adjacency matrix is going to be easy to describe procedurally, but we really don't want to write out all of those 100 entries one at a time. And so for that, we'll turn to Python.